network intrusion, so cybersecurity attacks, map them from their tabular features into images and score them. So essentially you can think of it as fingerprinting an attack. And it will show different motivations for why this is, but these are 16 by 16 thumbnails in pixel space, so 256 total features. And here's a denial of service, here's a backdoor attack, and here's normal. And we want to use standard image classification techniques to score the type of attack. So the outline is, what problem are we trying to solve? What methods can we use to take advantage of computer vision in tabular cyber data? We'll show our results and some conclusions for future work. So the motivations, why would you want to take complicated features already, such as duration of attack or a number of bytes between machines, and convert it into an image? And if you think of the progress in deep learning since 2012, the initial thrust of deep learning really was image-based, and then about 2018, language really started to take off. But the laggards in kind of standard problems are still audio lags a little bit in terms of its time-dependent structural data and tabular data, which the vast majority of traditional statistical machine learning has kind of always been tabular, matrices, et cetera. Well, so you also are probably familiar with the MNIST digit database. It's everyone's favorite. If an algorithm doesn't work on MNIST, it's likely not going to work on more complicated domains. And there are various iterations of this. This is one called Fashion MNIST. We've done one of overhead satellite imagery called Overhead MNIST. But the basic notion is you take a small feature set and begin to analyze it as an image set. So what we're going to do is translate the tabular data into a similar format. So the goodness of that is you inherit all of the vast literature. I think there are about 40 or 50,000 publications just on MNIST and about 20,000 just this year. So this remains still kind of the most active, not without criticism, but a handwriting digit recognition is a pretty standard use case. I include one other image down here, which is an audio spectrogram. And this is kind of the motivation. Audio is a hard problem. Speech recognition is a hard problem. And so a lot of researchers have essentially taken the trick or the hack of converting this into an image and then using that to classify the audio. And we're going to do that in a tabular sense. So the data set we're using is a sort of famous one out of University of New South Wales in Australia. And this was a follow-on to a 1999 data set that kind of became aged and dated, but you basically generate a network attacks. You have a traffic generator, you have a couple servers, one may host malware, and you're going to capture network packets. So this could be hundreds of gigs of packet capture files. After that, this 100 gigabytes of raw network traffic eventually gets pushed through feature detection, and finally algorithms give you kind of the core features of what you would expect a connection machine to machine to look like. So for example, number of bytes sent, or time of connection, or recency of connection, et cetera. And so finally, the published data set is a comma separated value file with 49 features. We're going to unpack these 49 features into about 196. And then we're going to normalize those and flatten it to pixel values in an image. And that's our basic program. So the real core features, kind of uncorrelated, are about 42. Because 3 of them are categorical features, meaning non-numerical values, such as protocols, states, or services. So if you think of HTTP, FTP, each one of the columns of this data set will just have these have the label, and we want to do one-hot encoding, which means we'll create protocol TCP, and if it exists, we will call it a 1. If it doesn't exist, it will call us a 0. And so that blows out these 40-ish features that are independent into what we construct as a 16 by 16 image. And there's about 180,000 training or test examples. So really the core of the project is to create 250,000 images and then classify them. So this is our kind of layout table, if you will. There are 16 rows and 16 columns. As you see, when we one-hot encode a protocol, we attach protocol and essentially say, you know, this is FTP, this is secure service, this is secure shell. Here are the source and destination packets, their duration, etc. So really the only remaining question is, how are we going to put this in a grayscale image? And so we take the min max and basically scale the whole thing between 0 and 255 on the grayscale image. And finally, we get our 250,000 images to label. So these are, this kind of interested us because this is the same kind of footprint as MNIST. So you can imagine carrying over all of those into cybersecurity is attractive. Also inheriting, you know, not wasting your time doing things that are unlikely to work, such as, or are less likely to work, like some simple decision trees. But this is a fingerprint of normal traffic, scale between 0 and 255. So the whites here represent, let's say it's this is normal HTTP traffic for a certain period of time. Honestly, the arrangement of the light and dark is less relevant as long as it's uniform across all. Here's our 1 normal, and here are our 9 attack families. If you really think of it in the 0 to 9 digits, this is 0, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9. One thing you always encounter in this field is the unbalanced data set. So for example, out of the 250,000, there are really only 44 worms. And so that will turn out to be a difficult one to capture here. And you have to use all the traditional techniques of balancing the data set. So that's the high level view. We want to first separate normal from attack data. And then we want to tell which family of attack. Is it denial of service? Is it backdoor? Is it a fuzzer, reconnaissance, shellcode, or worm? Clearly, this is a good example of using abstract machine learning in a place a human analyst is unlikely to distinguish the differences and the subtleties here between, say, a reconnaissance attack and a fuzzer. But fortunately, deep learning is pretty good at this. So here's the interesting part of the way this data set was constructed. Unlike traditional training and testing split, the vast majority of the data set is reserved for testing. It is relatively balanced between normal and attack, but if you look at the families, here are the 44 worms, 37,000 normal traffic exchanges, and then half of them are exploits and generic. It's interesting that they reserve a tremendous amount of attack data to test. So obviously this is a benchmark, and everyone in machine learning loves benchmarks. So what has previous work done on this? These are kind of 4 favorites: random forest, decision tree, naive Bayes, and support vector machine. So clearly, just in terms of raw accuracy, Bayesian is not as good here, but clearly you can get in the high 90s. And this is 2018, but this is really working on the tabular data. So traditional random forest will break up that into subsections, build many decision trees, and then let them vote. So this looks pretty promising as a start. One of the beauties of addressing, in our case, we actually end up with 196 features, is if you run random forest, you can immediately score the contribution of each variable. So feature importance or variable importance often is as interesting as the raw accuracy. In this case, of the 196 features, the #1 feature here, and the way it's done is you basically take one feature out, solve the problem, and see the accuracy go down. And if the accuracy goes down a lot without that variable, then it obviously contributes significantly to the classification. In this case, source to destination, time to live value. sort of the definition of a connection, and there's some other ones here like percent from a given IP. The beauty of this is these 12 can give you a decent score in summary. But we're going to treat the whole problem as just another example of MNIST or handwriting recognition or fashion MNIST. We also are going to introduce a nice trick, which is to do transfer learning. So even though this is pretty significant amount of training data, as 250,000 images, some of the classes are unrepresented, and you can take advantage of, in this case, MobileNet V2 is a very popular pre-trained architecture, and you just change the last label layer, and you inherit potentially the hierarchy that's been created by training on other data sets. So this is essentially a pre-trained expert, but moved to a different domain. The one thing I will point out about the architecture is it is looking in small sections of the image. So a 3x3 convolution means if you go back to the way we arrange the big matrix to the image, there's kind of a built-in assumption that things far apart in the image are not related. And that may come back to bite this technique, and certainly introduces the dependence of how do you know the right way to order the features if you're going to convert it that way. So here are our basic results. In the binary case, so we're not concerned about the family yet of attack, and just normal to attack, it's a balanced data set, so accuracy can make some sense. In the test case, we can get 97 to 98%. There is a 2020 paper on the same thing where it's a similar confusion matrix, but they're at 91% for the normal and 99.2% for the attack. This is a smaller data set because they're interested in edge examples for detection. So like an IoT thermostat or something. Another version of this, which is from 2019, we significantly exceed that. We're 98%, 97%, they're 98 and 0.85. The reason I introduced this one is because this is really training from scratch. In the tabular case, we're still not dealing with images in this. So that is one potential interest area for using images for tabular data. The second one is it's not taking advantage of transfer learning, which is not clear how you do that in a tabular data set. So we think those are the two primary motivators here: is map it to an image, take advantage of the convolutions, and then build on the hierarchy that exists already within the trained network. So now we want to do the multi-class problem. We know we're being attacked, and so we want to classify the family of attack, and we also want to test our dependence on the size of the test data set. So typically in these families, here's our normal. We're pretty good at these highly represented cases, 98%, 96% in the multi-class problem. We do see some dependence on the training size. So as you imagine, we get more and more examples. The kind of cliche is we should get better at this. Clearly, we're not very good at underrepresented classes, and that's eventually going to define the average classification success. This is pretty good simply because there are, let's say we know we're getting a denial of service attack. The usefulness there is I can set a firewall rule or something, an IP block. And so clearly your recommended courses of action under a denial of service are different from someone saying exploring your network or setting up a backdoor. So that's really the reason as an analyst you want to know not just am I being attacked, but what is it and how can I respond? So this is the sort of standard confusion matrix by class. So this is the actual we know from the training or the test set, the labeled test set from the exercise, and this is the predicted. You clearly want to always live on this diagonal. We see where we're getting spread here, oftentimes across areas where I guess the attack is similar both in nature. So reconnaissance can be a feature of worms, etc. This is kind of the state of the art. Everyone, we want to compare this image-based technique, which we think is quite generic, against traditional tabular statistical machine learning. So this is other people have published sort of the 70 to 76% for the multi-class case. Clearly, normal is pretty high, and we prove here on the bottom. Our current results are pretty good at distinguishing normal from attack in image space. And then, it varies across the board. We're no good at worms, which really affects our overall accuracy. But clearly, you could do this in a multi-step way. You could also have standard ensembles of voters who basically take normal out once you decide it's an attack, and then you can get better fidelity on these other ones. So the summary of this work is like what people have done previously in audio. We think tabular is a candidate, along with others, for converting to image thumbnails. Microsoft and Intel have an existing program that basically converts the first 1024 bytes of viruses to images, and then they use that to classify the type of virus from image space. Just by reading the header of the virus itself. So clearly, just like audio, converting tabular to image is an interesting technique. We've put this data set on Kaggle, so you can download it or watch other people compete on this data set. We do recognize there's a shortcoming in this approach, like how are we going to handle the ordering of the data set? It may turn out you want to separate related images, essentially related parts of the features, to not allow them to cluster them together. That would be making it harder potentially for the image classifier. You also may want to cluster them, so maybe two features now become uncorrelated. So this dependency on the order is something that exists, just like in audio, the dependence of a word order. The future is clearly there's a ton that we can learn from existing literature on MNIST. All that should transfer directly over. We can already know the answer to a lot of tabular solutions, and that's extreme gradient boost. Those kind of decision trees that focus their attention on the hard to solve problems typically outperform. And like the previous speaker, we think there's a tremendous amount of potential to take the existing literature on generative adversarial networks to potentially define new parts of the classification space. So if you look at the underrepresented case of worms, we can take those images, do generative images for examples of more worms to balance the data set or potentially increase its diversity. So here, I'll close on this. Both data sets are available on Kaggle. The original New South Wales one is there from several years ago, and we posted this about a month ago as a challenge problem, and already people have put code up there. So with that, I'll take any questions you might have. Thank you.
Thank you very much for the presentation. It's very informative. Is there any question from forum?